Good morning to all. So, welcome to this 12th lecture of the course Fluid Mechanics. In the previous lecture, we have discussed the hydrodynamic forces which are acting on the submerged planar surfaces. Today, we will talk about the hydrodynamic forces acting on the curved surfaces. And if you recall from the last lecture, brief idea I had already given. So, let us consider that we have a completely submerged curved surface over here. This is our free surface of the liquid. So the one of the approach for finding out the forces is that we should determine pressure distribution acting at each and every point of this curved surface, and then we can multiply that with area and then do the area pressure into area integration for the entire curved surface. Okay. However, for complex geometries of the curved surfaces, this approach is actually very complex. So another alternative approach which I already introduced you in the previous lecture is that I can take the projections of this curved surface. For example, if I look from the side view, then this red colored line, whatever I have shown over here, this is nothing but is my curved surface, how it will be looking from the side view on a two-dimensional plane. Okay, and this side over here is I have nothing but the vertical projection of this curved surface, and this particular line over here is actually horizontal projection of the curved surface. Now, as per the second approach, what I can do is actually I can take the volume of the liquid which is just resting over this curved surface. So I have considered that volume of liquid, and with the help of this blue colored dashed line, I have nothing but drawn a control volume over here. Now, if I can estimate what are the forces acting on this control volume, then I can actually ultimately determine the forces which this liquid is applying on the curved surface. So, this approach also I told you in the previous lecture, that if I have a curved surface, so this curved surface, say if it is experiencing Fr amount of resultant force from the liquid, then ultimately it will supply similar amount of reaction force on the liquid. So that is something which I have done over here. So I have taken this control volume, and on this control volume I am considering that Fr amount of resultant force is something which is subjected on the liquid control volume by this curved surface. Okay, so is it clear up to this point? So this is nothing but coming from the Newton's third law, because as per the Newton's third law, if there is certain action, there will be the equal amount of reaction also. So action is that liquid is subjecting Fr amount of force on the curved surface, and its reaction, we are saying that curved surface is actually subjecting equivalent amount of resultant force but in the opposite direction. Okay, now this Fr is having two components. One is Fh, horizontal component, and another is Fv, which is the vertical component. Okay, now let us consider that this vertical projection of the surface is nothing but I have considered a planar surface. This is my assumption. Okay, so if you have a curved surface, then the vertical projection of curved surface will nothing but a horizontal plane. Okay, and this horizontal planar surface I have assumed over here, the vertical projection will be a planar surface. So this is the vertical planar surface which I have considered over here, and let us consider that on this vertical planar projection which is over here, it is actually experiencing Fx amount of force because of the liquid. So because it is completely oriented in the vertical direction, so any pressure which will be acting on this projected surface, that will be normal to the surface. So that is why the resultant force which will be acting on this vertical projected plane, that will be in the horizontal direction. Okay, likewise I have this horizontal projection. This horizontal projection will also be a nothing but a planar surface, and of course whatever the width of this planar surface is there in the third dimension, that will be normal to the board in our particular case. Okay, so here because it is already submerged within the free surface. So of course the magnitude of the pressure will be slightly higher than the free surface pressure depending upon its depth. So that's why I am considering, say, whatever this black colored pressure distribution I have drawn over here, because now the projection is horizontal and we are not changing the elevation for horizontal projected area. So as we are not changing the elevation, that's why at each and every point the magnitude of the pressure will be the same. Okay, and say this is contributing to some resultant force Fy over here. Okay, now we are considering this control volume of the liquid. So this particular control volume of the liquid will be having certain amount of weight also. So say W is its weight. Okay, so now what I can do, I have to calculate Fx, Fy, and if I calculate the Fx and Fy, if I know these two forces, then by just doing the force balance in equilibrium position for this control volume of the liquid, I can actually determine the values of forces Fh and Fy. So is this one clear to all? Okay, let's now see how to calculate Fx and Fy. Okay. So to calculate Fx, as I told, it is nothing but a planar projection. Okay, so I can assume it of a plane surface, and for this plane surface I can utilize the principles whatever we have studied in the previous class. Okay, so what were the principles which we studied in the previous class? That is how to determine forces on submerged planar surfaces. So this thing I know from the previous class. Once I know this thing, then ultimately actually I can determine the Fx. So I have this value of known on a planar surface, because this vertical projection is nothing but a planar surface, and this planar surface is completely submerged in water. So as it is completely submerged in water, so whatever the theories I have told you in the previous class, same I can apply and I can determine the value of Fx. Okay, and along with the value of the Fx, I can even determine its line of action also. Okay, so how line of action I can calculate? Y center of pressure for the force which is acting in x direction. Okay, so this is how I can determine the y coordinate of this particular force also, means the line of action of this force. Okay, now what I can do, if I consider the sum of forces in x direction, or I can say more precisely, because x I am using symbol for Fx also, so I can say sum of forces in horizontal direction equal to 0, then I will be finding that from the left face Fh amount of force is acting, and from the right face I have minus Fx amount of force which is acting, and this is equal to 0. So from here I can simply say that Fh is equal to Fx. So the meaning is, if I can calculate the force which is acting on this vertical submerged plane of the curved surface in x direction, that will be giving me the horizontal component of the resultant force Fh. Okay, so this is how I can calculate Fh. Now let's talk about Fv. So for determining Fv, I have to now consider the force balance in vertical direction. So sum of all forces in vertical direction is equal to 0. So F vertical equal to 0 gives me Fv is the force which is acting in upward direction, minus W is the weight which is acting in downward direction, minus Fy is the force which is acting at this particular control surface, which is nothing but the horizontal projection. Okay, so on this horizontal projection of the liquid control volume, I have Fy amount of force. So that I have also considered over here, and this is equal to 0. So from here I can simply say that Fv is nothing but equal to Fy plus W. Okay, so W weight is very easy to determine. We have to just determine the volume of this particular control volume, and I can multiply it with the density of the liquid and the gravitational field. Okay, and to determine Fy is also important, very easy. So if I say that, say S is my distance up to which it is submerged, then my total pressure which is acting at this point, that will become P equal to nothing but P naught, if P naught is the pressure above the free surface, plus rho Gs. And now how I can determine Fy? Fy will be nothing but equal to P times into area of horizontal projected surface, area of horizontal projection. Okay, so this is how I can determine the Fy amount of force. And of course, the line of action of this Fy force will be at the center of the control volume. And same is also true for the weight. So weight will be acting at nothing but the centroid, because this particular geometry is nothing but this control volume is containing a liquid of homogeneous density. We are not considering the changes in density with elevation. So that is the reason, if I consider homogeneous density, then whatever will be the geometric centroid of this control volume, same will be its center of gravity. Okay, so this is how I can determine the line of action of these individual forces as well. And once I know Fy and weight, I can calculate the value of Fv. Okay, so now if I know Fv and Fx, I can simply determine the resultant force Fr is nothing but square root of Fx square plus Fy square. Okay, so this is my total resultant force, which is supplied by this particular, submerged curved surface on the liquid volume. Okay, so from Newton's third law, the same will be the magnitude of force, but in opposite direction. Okay, but till now, whenever we have calculated this resultant force, we have not yet determined its line of action, whether it will be acting at this point, or at which point. So how to determine that? What we can do is, I can find out individually the line of action of all these forces. For example, by knowing ypx, I can calculate the line of action of the fx force. I can calculate the line of action of fy, line of action of w, and then by taking moment about some point, okay, I can nothing but calculate the line of action of this particular force Fr. Okay, so how to do this? That we will try to do with the help of a numerical problem. Okay, so whenever we will be studying some numerical problem, then I will tell you how we can take this moment in order to determine the line of action of this particular resultant force. Okay, but you must know that in this particular subject of fluid mechanics, over here majority of the time in the classes I am mainly talking about the fundamental concepts. Okay, and depending upon the distribution, because we have tutorial after every 5 lectures, so number of tutorials are less, so that is the reason that we are practicing slightly lesser number of problems in the classes. So it is what I advise to all of you, that you have 2 textbooks I have specified. One is Senjal and Simbala, and second is FM White. Please do solve their example problems, and once examples are done, then go for the solving the unsolved problems. Okay, so till this point, no one of you have reported me that you are facing difficulty in solving the numerical problems. So please focus on this aspect. Okay, so after completing this second module in the next class, I will also give you one assignment, detailed assignment based on the module 1 and 2, but you people also practice more and more problems, because in exams you will be finding mostly the problems. Okay. Okay, so there is one more interesting concept which is related to this topic. So that is, till now we have studied that surface is submerged inside a liquid of same density. Okay, now if we have a submerged surface, but part of the surface is in one fluid and part of the surface is in other fluid, then what will be happening? So let's try to see that situation. Okay, so if I consider that this is my free surface and this is my object. Okay, and let's consider that up to this distance, say this is B1 distance of this object, it is nothing but submerged inside a liquid of density rho. Okay, and below this, say B2 portion of the liquid is nothing but it is submerged in another liquid of density rho. Okay, so can you tell me out of this rho 1 and rho 2 which one should be larger? Yes, of course, rho 2 has to be greater than rho 1, because if rho 2 is greater than rho 1, then only we will be finding that in a external gravitational field, this situation will be existing in this interface, steadily this interface between liquid 1 and liquid 2 will be existing. If density of 1 is less than density of 2, then our heavier fluid is at the top, and this is not a stable configuration, and this will lead to the liquid 1 to move in downward direction and liquid 2 to rise in upward direction, and this stratification to happen. Okay, but this is the stable situation. Okay, so if you have this type of situation, then how to determine the forces which are acting on the body? Okay, so one point is obvious. Say this point is, this is submerged through certain height S. Okay, so if it is submerged through certain height S, then of course if outside pressure is P naught, so at this point my pressure will be P naught plus rho gs. Okay, so say this is the pressure. Now because pressure acts always normal to the body, so that is why I am drawing the arrow for showing the pressure, something like this. Now up to this point, of course I will be having distribution of pressure, and it will be having certain increasing trend. Okay, because whenever I am moving ahead, I am reaching to the more deeper points. So when I am reaching to the more deeper points, pressure is actually linearly increasing with the magnitude rho 1 g times depth. Okay, so that's why this is my, say, distribution of pressure up to this point. But what will happen after this point? After this point also pressure will be increasing, but older rate of pressure increase was like this. But after this point, my density of the fluid has changed. Now density is not rho 1, but it is rho 2. So when density is rho 2, then this rho 2 gs quantity will give me a larger rate of increase with the depth. So if I have larger rate of increase with the depth, so I will be finding that the slope of this pressure change will be increasing, and ultimately my pressure distribution will be something like this. Okay, so that is my pressure distribution. So this is new pressure distribution over here. Okay, so now you can see that in up to B1 distance of the body, I have other pressure distribution, and after that my pressure distribution is actually something different. Okay, so of course the magnitude of the forces will also be different. Okay, so how to determine the forces for such compound situation? It is very simple. What I can do, I can first divide the body into two parts, and then simply I can actually apply the principle of superposition. Okay, so what I can do, first I can consider that this is my free surface. First I can consider that at angle theta and up to distance b1, I have nothing but a body, and it is submerged in fluid of density rho. Okay, so if I consider this situation, and let us consider that the resultant force acting on this body is nothing but FR1. Okay, and what is the magnitude of this FR1? The magnitude of FR1 will be nothing but, if say this is the centroid of the body, C1 is the centroid, then what is the value of pressure at centroid? So PC1 times area of body 1. So I am using this subscript A1 because I am now talking about body 1. Okay, so this will be my resultant force FR1, which is acting on this first portion of the body, and of course the line of action of this will be yp1, which I can easily calculate from the formulation which I have described you in the previous lecture. Okay, so up to this point we have calculated. Now similarly we have one more body. So for that what I can do, I can consider that this is my free surface. Now at an angle theta I have another body submerged whose width is b2. Okay, and up to this point I have density rho1, and below this I have density rho2. Okay, so I must know the distribution of the density, because up to this point whenever I will be calculating the pressure, I have to use, say if S1 is the total submergence now, so I have to use P0 plus rho1 G1 S1 up to this point. So this will be the pressure. Here, say I am talking of writing it as P1 is nothing but equal to P0 plus rho1 G1 S1. And after that, say its centroid is lying at this point. This is my C2. So from this point to this point, okay, there is now the density is rho2. So when I will be calculating P2, that will be nothing but P1 plus rho2 G, and let us consider from this point my centroid location is at HC distance, HC2 distance. So this distance is HC2, so it will be HC2. So that is the nothing but P2 is nothing but centroid pressure of body 2. Okay, so now for this body, my line of action of the force will be somewhere over here below the centroid, Fr2, and the magnitude of this Fr2 will be nothing but pressure at centroid of the second body times area of the second body. Okay, so this is how I can calculate the individual magnitude of the forces Fr1 and Fr2. Okay, so now if you see, and similarly for this also I can determine Yp2. The Yp2 is nothing but the center of pressure for body 2. Okay, so center of pressure, which also shows the line of action of the resultant force, that also I can determine nothing but from the formulation discussed in the previous lecture. Okay, so now I have Yp1, I have Yp2, I have Fr2, and I have Fr1. Okay, so now when I have Fr2 and Fr1, what I can do basically, once I have Fr1 and Fr2, what I can do basically, I can determine the net resultant force, which will be nothing but Fr1 plus Fr2. Okay, why net resultant force will be just summation? Because the direction of both Fr1 and Fr1 is actually same, and these forces are parallel to each other. Okay, so as their direction, they are pointing in the same direction. That's why by using the vector algebra, I can simply write that net resultant force Fr will be equal to Fr1 plus Fr2. Okay, so similarly, if I have n number of bodies, n number of liquid layers, so then I can simply write that Fr will be nothing but sum of the forces I varies from 1 to n into Fri. Okay, and how Fri can be calculated? Nothing but pressure at the centroid of, by calculating pressure at the centroid of ith body multiplied by area of the ith body. Okay, so this is how I can generalize this equation if I have n layers of liquid for a system. Okay, now one more point is remaining. We have determined the magnitude of individual Fr1 and Fr2, and we have taken its help to calculate the net resultant force Fr. Okay, but how this net resultant force Fr is acting, or in other words, what is its line of action or center of pressure? So how to determine that? So this is quite obvious that in the bottom portion pressure distribution is more, and in the top portion pressure magnitude is actually less. Okay, so what I can do is I can consider that somewhere over here, say this is my line of action of Fr2, this is my line of action of Fr1, and somewhere over here, say this is my line of action of net resultant force Fr. Okay, so if distance from this point to Fr is Yp, from Fr1 distance is Yp1, and from Fr2 distance is nothing but Yp2. Then what I can do now, I can take the moment about this point O, and my net resultant force should give the same amount of the moment as the moment applied by the individual forces. Okay, so ultimately by taking the moment, I can say that Fr into Yp will be equal to Fr1 into Yp1 plus Fr2 into Yp2. Okay, so ultimately for a system of n different liquid layers, I can write that the resultant force, which is nothing but summation of I varies from 1 to n PCI into AI, okay, multiplied by Yp will be equal to summation of I varies from 1 to n into Fri and Yi. So it means Fri is PCI into AI. This is nothing but Fri, and also this has to be multiplied with Ypi. Okay, so entire summation of this. So this will be giving me nothing but the center of pressure, or I can say the line of action of the net resultant force. Okay, so this is very important concept, and it can be employed in many other situations. Okay, just one point I forgot to tell you, which I would like to now discuss particularly regarding the curved surfaces. So when we studied the curved surface, we may have one situation where curved surface is oriented something like this. Okay, so if this is the situation of curved surface, then whatever the liquid control volume I will be drawing, that will be something like this. Okay, so one point of this type of curved surface is that whenever I will be calculating the force in vertical direction, so of course it will be applying pressure on this on this horizontal projection. So on this horizontal projection I will be facing some pressure, okay, but I will not be facing any weight of the liquid which is acting on this curved surface. Okay, so whenever I will be writing, say Fv is the vertical force, so Fv will be directly equal to Fy. So if Fy is the force over here. Okay, so here weight will not come into picture. So what I can say that in over the horizontal projection of the upward facing curved surface, okay, upward facing curved surface. So on upward facing curved surface, weight will not come into picture. Whose weight? Weight of liquid. Okay, so that is an important point. Okay, another important aspect is that if I have a curved surface which is nothing but forming either arc or say semicircle, part of a circle. Okay, so for this curved surface, if you see the distribution of the pressure, it will be something like this. Always pressure acts normal. So but its magnitude, as we are moving into the deeper locations, its magnitude will keep on increasing. Okay, so this will be my distribution of the pressure. Direction of all the arrows will be normal to the curve. However, its magnitude will keep on increasing as we are moving in the downward direction. Okay, so now you will be finding that from the entire body, whatever the forces are acting because of the pressure, these must pass through nothing but a common point, and that common point is nothing but the center of the circle. Okay, so whatever the forces now which are acting because of this pressure distribution on an arc which is forming part of a circle, okay, or a semicircular surface, all these forces are nothing but of concurrent nature, because these are passing through a same point. So that's why all these forces are nothing but of the concurrent in nature. Okay, now these concurrent forces, whatever the resultant will produce, that resultant must also pass through the center of the circle. Okay, because the line of action of the individual forces is passing through the circle, whatever are distributed over the entire body. So that's why that particular resultant force should also pass through the center. But where it should be located? Should it be located in this exactly horizontal plane, or should it be below the horizontal plane? Can you answer? Yes, correctly answered. So, seeing the distribution of the pressure, because in more deeper portions, the force is actually more. Okay, so that is why the line of action of the force will be somewhere over here. However, it must pass through the center of the circle. Okay, through which this particular arc of curved surface is being formed. Okay, so this is one important point. Okay. Now, after discussing the forces on the submerged bodies, there is one another important concept which is particularly called as the concept of buoyancy force. Okay, and this is really important in defining the stability of the submerged and the floating objects. Okay, so first let's understand what is buoyancy. So to understand the buoyancy, we will be considering that I have a free surface, and below this free surface any arbitrary disc shaped body of area A which is having constant thickness h, which is having constant thickness H is actually submerged inside a liquid. Okay, and say the top surface of this is at submergence depth of S from the free surface. Okay, so now if I look into the side view, in the side view this will be looking like a simple planar surface of thickness H. Okay, so now what will be happening? For this particular planar surface, I will be finding that from the top side there is a pressure. If I take in gauge scale, say I am not considering the P naught value, then which is acting at the free surface. So if I not consider this P naught value, if I take in gauge scale, then I can say the magnitude of this pressure will be rho g into S. Okay. At the same point of time, there will be some pressure acting from the bottom side, and if you see, whenever I am drawing the pressure from the bottom side, actually I am taking the size of the arrow as slightly larger. Okay, so the reason is that because this bottom face is at more depth h below the water, so that's why this bottom portion will be having more pressure, and that pressure will be rho g of S plus h. Is this not clear? Now this is a planar disc. Okay, so if you see, this particular disc over here is subjected to net upward force because the bottom pressure is more in comparison to the top pressure. So that is why the net force which is acting in upward direction, in vertically upward direction, that is nothing but equal to rho times g into S plus h times area, say area of this particular body, minus rho gs is acting in downward direction multiplied by area. So ultimately this vertical force which is acting in upward direction is actually rho g h into A. Okay. Now over here if you see, h into A forms nothing but the volume. A is area and area times h, constant thickness, that forms the volume. So I can simply write it as rho v into g. Okay. So where rho is nothing but density of the fluid, because when we are considering, so we are considering this rho to be density of the fluid. Okay. And this is volume of this particular container, and g is gravity. So this vertical force which is acting on the body in vertical upward direction, this particular force we call as nothing but buoyancy force. So Fv is equal to Fv, and which is equal to rho v g. Okay. So this is one important finding, and this vertical force we are calling as buoyancy force. So it means that when a body is submerged in a liquid, it is experiencing different amount of pressure at its different locations depending upon the depth of these locations within the body. Okay, and ultimately, because more deeper locations, these are subjected to the higher pressure, it is experiencing some upward force in the vertical direction. Okay, and the magnitude of that upward force is nothing but rho v times g, where if you see v is volume of the body, rho is density of the fluid, and g is gravitational force. So ultimately, the vertical upward force which is acting on the body, that is only dependent upon volume of the body, because here density of the fluid is coming into picture. Okay, so it is not depending upon the density of the body. Okay, so if this disc is made up of iron, or if it is made up of aluminium, or even of wood, or it is nothing but a hollow body, we have a hollow body of this disc, all these will be experiencing the same amount of buoyancy force. Okay, so it means the buoyancy force acting on the body nothing but depends upon amount of volume of that particular. It does not depend upon the density of the body. Okay, and ultimately, if you see what we are considering, we are saying that whatever the volume of the body we have considered, that is equal to, we are multiplying that with the density of the fluid. So it means this V volume of the body is coming into the fluid, and ultimately what it is doing, it is displacing this much volume of the fluid, and that displaced volume of the fluid when multiplied with density of the fluid and gravitational field is actually giving rise to a force which is acting in the upward direction. So what I can say ultimately, that the buoyancy force is nothing but equal to the force due to volume of fluid displaced. Okay, so whatever volume of the fluid is displaced, actually equivalent to that force is acting in the vertical direction. And this equation is nothing but a famous principle which is called as Archimedes principle, which says that the buoyancy force acting on a body is nothing but the weight of the liquid which is displaced by the body. Okay, so for example, if I talk about human body, okay, so we are also displacing nothing but atmospheric air. This entire atmosphere is actually filled with air. So if I am standing over here, what I am doing is actually I am displacing this air, and volume of my body is taking the space of the air. So it means that on me also there must be some sort of buoyancy forces which must act in vertical upward direction. Okay, so on an average basis, for a human body, its volume can be equated close to 0.1 meter cube, and if I consider the volume of air displaced at 0.1 meter cube under the atmospheric pressure conditions, then this will give me buoyancy force for human body equal to 1.2 Newton, close to 1.2 Newton. Okay, so it means that whenever we do measure our weight by using some weighing machine in the atmospheric condition, there is error of 1.2 Newton in measurement of our weight. So ultimately 1.2 Newton force is approximated, 1.2 Newton force is acting on us in the upward direction. So our weight is nothing but 1 Newton more in magnitude in comparison to what usually our machines are actually measuring. Okay, is this point clear? So if we include this correction, then we will be having our error in the measurement of weight in the range of something about 0.15%. So very small error, roughly for a person whose weight is whose mass is 80 kg and weight will be 18 to 9.8. Okay, so for a person of 80 kg, if we introduce this error in the weight, then it comes out to be about 0.15%, which is very small on the engineering calculations. Okay, so that is the reason we many times neglect this. Okay. Now, this buoyancy force is having many implications. Okay. For example, if I talk about, let's say I have a pool, and in this pool, if I have some body, so over this body, its weight is acting in downward direction and its volume is acting in, buoyancy force is acting in the upward direction. Okay. So ultimately, this particular body will be in equilibrium only if sum of forces is equal to 0. Then only this body will be in equilibrium. So to make sum of forces equal to 0, my buoyancy force must be equal to the weight of the body. Okay, so then only this will be in equilibrium. Now, this body can be either completely submerged or this particular body can be partially submerged. This situation may be something like this. Okay, so it is not fully displacing the water, but part of the volume of the body is actually displacing. So let's consider that below this, the portion of the body which is displacing the liquid, we call this as submerged volume, and the total volume of the body is nothing but V. Okay, so now if I talk about the buoyancy force, because buoyancy force is nothing but equal to the volume of the liquid displaced. Okay, so volume of the liquid displaced will be density of the liquid is rho times submerged volume times g, and weight of the body on the other hand, say rho s is the density of the body, so rho s times total volume of the body is V and G. Okay, so from here Gg will be cancelling, and one important quantity I will be finding that V submerged divided by total volume is nothing but equal to density of the body divided by density of the fluid. Okay, so this is one important ratio. Now, this ratio of submerged volume by total volume gives us three different combinations. Okay, so the first combination is that if my rho s is less than rho. If my rho s is less than rho, then of course V submerged will be less than V total. Okay, so in this situation I will be finding that if this is my free surface, then body is not completely submerged, but it is only displacing portion of the fluid medium. So this is called as nothing but a floating body situation. So this is a floating body situation. Okay. On contrary, I can have a situation where this is my free surface and density of S is equal to rho. So when density of S is equal to rho, then my submerged volume will be equal to total volume. So in this situation, my body must be completely submerged. However, its buoyancy force will be equal to the weight. So in this situation, if I place the body over here also it can stay. If I place body to any other location which may have different depths involved, here also it can stay. It can stay to more deeper location. So at any position, if you say move body from one point to other point, it will stay there itself. Okay, whether you displace the body to whatever depth, anywhere you put this body, if you displace this body, then what will be happening? If I try to move this body in downward direction, so it means I am increasing the submerged volume. Okay, but it will try to resist to decrease the submerged volume, and it will try to maintain the ratio of rho s by rho to reach submerged volume by total volume. Okay, so that is something which will happen if I have a floating object, and if I displace this floating object in vertically downward direction, this floating object oscillates for some duration and once again reaches to its original equilibrium position. So that is the concept of a floating body. But on contrary, if I have a neutrally buoyant body, okay, so this type of body is called as neutrally buoyant body. The meaning of neutrally buoyant body is that density of the body is equal to density of the density of the fluid. So in this situation, submerged volume will be equal to volume. So now, in any of these combinations, everywhere my submerged volume is equal to the total volume of the body. Okay. So in this situation, everywhere I will be finding that body will stay at its position. So even if I displace from this point to this point, here also it is having the equilibrium position, so here also it can stay. If I move from here to here, there also it can stay. So this type of situation is nothing but called as the situation of a neutrally buoyant object. Okay, and these neutrally buoyant particles are used in many advanced flow measurement techniques to determine the velocity field. Okay, because whenever these are put into the fluid, these does not show their any individual flow hydrodynamics. Okay, they try to follow the behavior of the fluid. So as they neutrally try to follow the behavior of the fluid, by tracking these particles, one can determine the velocity field of the flowing system. Okay, so this is the important application of neutrally buoyant particles in many areas such as particle tracking velocimetry and particle image velocimetry (PIV), which are nothing but the advanced tools to experimentally determine the velocity distribution. Okay, so now we can go to third situation where density of the body is greater than density of the fluid. So in this situation, if you see, when rho s is greater than rho, then V submerged by V will try to become greater than 1. But this cannot happen. So because of this, our weight will always be greater in comparison to the buoyancy force, and we see that if I have this as a free surface and if I place any object of this type, this object will try to move down and it will keep on moving down unless or until it finds another solid surface or solid boundary to support its weight. Okay, so this type of a situation is called as sinking body. So here body will be completely sinking within the medium. Okay, is this point clear? Now, whenever we have studied this motion, so we have seen that I can have floating body, neutrally buoyant body, and I can have sinking body. But another important aspect which is associated with buoyancy force is nothing but the aspect of the stability. Okay, so whatever the bodies we are talking about, these must be stable. So whenever we are talking about the stability, first we will talk about stability of completely submerged objects, and after that we will talk about the stability of the partially submerged or floating objects. Okay, so say I have a completely submerged object and this is my free surface and I have say completely submerged object. Okay, now before discussing this concept of stability, I must discuss another important point which is called as center of buoyancy. So what is center of buoyancy? The way we defined center of pressure. Okay, so what was center of pressure was nothing but the point on the submerged body where the line of action of the resultant force is actually acting. So in a similar way, because this particular body is also subjected to distribution of the pressure, but it will be having a single point along which actually buoyancy force is acting. Okay, so if I have this situation where my body is completely submerged, so there I will be finding that whatever the geometric centroid of the body is there, so at this centroid my buoyancy force will be acting in the upward direction. So I can say this as nothing but the center of buoyancy of this body. Okay, on contrary, if I have floating object, then buoyancy force is only generated because of this much portion. Okay, it is not generated because of the entire body, but it is generated only because of the submerged portion or submerged volume of the body which is actually displacing the liquid. So because of this, now the centroid of, I have to consider the centroid of only the submerged portion of the body. So if I consider the centroid of the submerged portion of the body, that will be acting somewhere over here. So now my new center of buoyancy will be like this. Okay. So to explain in once again in very easy sense, what I can say is whatever the submerged volume of the body I am having, if I simply take the geometric centroid of that submerged volume, that will be giving me the line of action of the buoyancy force, and that line of action of buoyancy force is something which is called as center of buoyancy. Okay, so whenever we will be talking about the stability of a body, then center of buoyancy is having actually strong role to play. Okay, so now let us discuss that I have a completely submerged body, and let's consider that this particular body is of actually homogeneous density. Homogeneous density means at its each and every location the value of density is same. So if this body is of homogeneous density, then can you tell me where its center of gravity will lie? So if you have a sphere, and sphere is made in such a way so that it is having same density everywhere, say a copper ball or a steel ball, so you will be finding that whatever its geometric centroid, that will be nothing but the center of gravity of the body also, where the net weight is acting in downward direction. So if I have homogeneous density, then this point, say I am calling it as C, where C is nothing but my center of gravity. Okay, so on this center of gravity, my weight will be acting in downward direction, W. Okay, at the same point of time, say as this body is actually completely submerged, so if it is completely submerged, then whatever is its geometric centroid, that will be nothing but the center of buoyancy. And say I am calling center of buoyancy as point B. So in this situation, my point C and point B are coinciding. Okay, and at this center of buoyancy, my buoyancy force is acting in the upward direction, F. Okay, so I have a body of homogeneous density whose center of gravity and center of buoyancy both are acting nothing but at the centroid. So if both are acting at the centroid of the body, then the line of action or point of action of the weight and point of action of the buoyancy force both are same and in opposite direction. Okay, so now for this type of body, if I give any angular displacement, say if I displace this body through angle delta theta, then after the rotation also, if I draw the body over here, after the rotation also, if body is of symmetric shape, then its centroid will not change, and ultimately I will be finding that again the center of again the weight and the buoyancy force will be acting at the same point and in the same direction. So because of this, I will be finding that even I am displacing the body through angular displacement d theta. So now say the original point which was earlier oriented in vertical orientation, now it is at certain angle d theta, but there also it is in the stable situation. Okay, because there is no unbalanced force or movement which is acting on the body. So this type of situation is called as completely stable situation. So I can say that for a fully submerged body, if center of buoyancy and center of gravity are acting on a same point, then my situation will be completely stable. On contrary, if I consider that I have a body which is fully submerged, but the distribution of its weight is not homogeneous. It has higher density near the top portion, and near the bottom portion its density is low. So in this situation, I will be finding that my center of gravity will be somewhere over here, where its weight is acting in downward direction. Okay. On contrary, its geometric centroid, which is nothing but the center of buoyancy, this will be B, exactly at the centroid of the body where my buoyancy force is acting. Now if here I displace this through certain angle delta theta, so I will be finding now that with the new orientation my weight is distributed something like this. This is the high density portion now. So I can say that center of gravity has shifted nearly in the rightward direction. So if center of gravity is shifting in the rightward direction, so I can say here is its center of gravity and this is where the weight is acting in downward direction. On contrary, the center of buoyancy has remained the same and I will be finding that Fv is acting over here because center of buoyancy is depending upon the amount of or distribution of the distributed volume. So the distribution of the distributed volume is not changing. So now you have the forces acting in opposite direction and some distance between these two forces. So you can see this is the horizontal distance between these two forces. Okay. If you see the magnified view, then in a magnified situation weight is acting like this at point C and buoyancy is acting like this at point B, and between point B and C I have some normal distance between the line of action. So because of this I will be finding here there will be a torque which will be acting on the body and this torque will try to displace this heavier portion in downward direction. So this is the torque which is called as overturning moment. So this movement which is now trying to displace the body down. Okay, while this movement is acting, it is trying to displace the body down. So this particular movement is called as overturning movement and it creates a unstable situation. Because when you are displacing the body by delta theta amount, it will create an overturning movement and this overturning movement will try to change completely the orientation of the body. Okay. On contrary, if you have the situation where body is oriented in such a way so that its higher density portion is lying near the bottom. Okay. So in this situation, say this was the centroid where weight is acting and this is the center of buoyancy B where buoyancy force is acting in upward direction. Now if I rotate this through angle delta theta, then I will be finding that my weight over here is slightly shifting to right. So of course the buoyancy force will remain at its original position, but centroid will shift up and weight will be acting, weight will be acting somewhere over here. Okay. So this is when I have displaced it through angle delta theta. So now I have displaced the body through delta theta something like this, but it is creating movement. It is creating movement. So you can see this is one force, this is other force. So movement is created in this direction. So this is my movement. So I am displacing the body in nothing but the clockwise direction, but movement is created in counterclockwise direction. So this type of movement which is originated in a direction opposite to the displacement of the body, that is called as nothing but restoring movement. Okay. And this restoring movement will try to bring the body once again to its original position, which is nothing but a stable situation. Okay. So one important conclusion I can make from this point, when you can see the unstable situation. So when both the center of buoyancy and center of gravity are coinciding to each other, then it's a completely purely stable situation. And when center of gravity is above the center of buoyancy, then we are finding an overturning movement and it's an unstable situation. But when center of buoyancy is lying above the center of gravity for a completely submerged body, then we are finding a restoring movement which will try to bring the body back to its original shape after delta theta amount of displacement is actually subjected to this body. Okay, so this is one important situation. So this is about the stability of the completely submerged bodies. Now we will talk about stability of floating bodies. So from the previous discussion, you can take one important takeaway that whenever I am having a situation of when I want to have a stable situation, for example, if you see a big balloon of helium, and whenever that helium balloon is actually rising in the upward direction, you can see the cage structure, the steel cage structure where we can put the more weight, that is always near the bottom portion of the balloon. Okay, in order to keep its center of gravity below the center of buoyancy, because then only we will be finding a stable situation. Okay, on contrary, now we can talk about the floating bodies. So in case of floating bodies, what will be happening? The body will be partially submerged and partially it will be out of the liquid. Okay, so I can draw, say, if I draw in the form of a cross section of a ship, something like this. Typically, whenever ship etc. are designed, these are designed in such a way so that their bottom portion is heavy. Okay, so if their bottom portion is heavy, then their center of gravity will be below and center of buoyancy will be at the higher locations, which will give the stability. Okay, so then I can say that, say, at this point my centroid is there where weight is acting in downward direction, and at this point, say, my B is there, center of buoyancy, uh, where buoyancy force is acting in the upward direction. Okay, so now this is a stable situation for a floating body. Now if I displace this body through angle delta theta, then what will be happening? My body will try to achieve some new situation. Okay, so now I have displaced this through certain angle, say delta theta. Okay, now because I am shifting the volume, so when I am shifting the volume, so ultimately my center of I am actually changing the submerged volume. So when I am changing the submerged volume, my, say, center of buoyancy has displaced to this point B dash, and center of gravity has moved to this point G. So of course here I will be having FV force, here I will be having weight in downward direction. Okay, so in this situation you can see that my buoyancy is acting in the upward direction and gravity is acting in the downward direction, and this is creating a movement something like this, and this movement is nothing but opposite to the displacement. So I can call this as a restoring movement. So this is nothing but a restoring movement over here. Okay, in this restoring movement, one interesting point is, if I extend the older line of action of the buoyancy force, so you can see that when the body was in perfect vertical orientation, then about its line of symmetry my buoyancy force was acting. So I can draw the line of symmetry as something like this. So this shape is drawn a little bit wrongly. Okay, so now you can see that this black line is nothing but the line of symmetry, and line of symmetry was the original line of action of the buoyancy force. So this was the original line of action of the buoyancy force, and new line of action of the buoyancy force is actually B dash point in vertical direction. So this is nothing but the new line of action of the buoyancy force. Now the intersection of older line of action of buoyancy force and the new line of action of buoyancy force is something which is called as M meta center. Okay, and distance from M to G, this distance mg is called as metacentric height. Okay, so this distance from M to G is something which is called as nothing but the metacentric height. Now you can see that when my metacenter is lying above the center of gravity, it means my metacentric height mg is positive, then I have weight and buoyancy acting in such a way that it is nothing but creating a restoring moment. Okay, so because of this restoring moment, even if I displace the body, it will come back to its original shape. Okay, on contrary, if I take a situation where I have too much displaced the body, now body is displaced but through larger angle. So in this situation, what will be happening? This will be my older line of action, and this older line of action is such that, say my centroid has reached this point, okay, and say this is the point B double dash of new center of buoyancy. So in this situation, the buoyancy force will act over here and weight will act over here. And this point over here, the intersection of the two, this will be nothing but my M meta center. Okay. Now the distance from C to M, or even I have written the center of gravity as G in the previous case, so let me write it as G. So this distance from M to G now will become negative. So when my mg is negative, so you can see that if I enlarge this portion, then my situation is something like this. Here I am having G, where weight is acting in downward direction. Here I am having B double dash, where buoyancy force is acting in upward direction, and these two are coinciding at point M. Now I have displaced body in this direction, and if you see, buoyancy force is acting in upward direction and G is acting in downward direction, so this also creating movement like this. So this is nothing but a overturning movement over here. So as it is a overturning movement, so it means that in this situation I will be having unstable floating object. So it means if I have my ship and if I give too much displacement to the ship, then I can have a situation if its center of gravity is going above the metacenter and metacentric height mg is becoming negative, then the movement which will be generated between the buoyancy and the center of gravity, that movement will be nothing but a overturning movement and it will be unstable. Okay, so you can see sometimes in movies also they show that whenever there are waves in the water, then our ship try to oscillate. Okay, and while it is oscillating, if the angle of oscillation is small, okay, amplitude of oscillation is small, then it stays stable. But if it is too much, then this type of situation will come where center of gravity will go above the metacenter, and the movement which will be acting, that will be nothing but a overturning movement, and that will be completely overturning or toppling the ship into the water. Okay. Now whenever we design the submarines, you can see submarine initially is at the surface of the water, then we take it to some deeper location, desired depths within the water, then it moves underwater, and once again whenever desired we actually try to bring it back to the original position. Okay, so this is one important thing. Can you tell me how we control the submarines? No, we don't make hollow volume, we don't make it lighter, but what we do is actually, first point is, in order to achieve the stability, we want to keep the center of gravity in the deeper portion. So if I want to keep the center of gravity in the bottommost positions of the object, what I will be doing, I will be actually keeping submarine, keeping the heavy portion of the submarine, such as its engine or other storage spaces, etc. in the bottommost location. Okay. And another point is, as you are saying that we can change the volume. So outer surface of the submarine is nothing but a rigid body. It is not a elastic surface which we can inflate to change its volume. So outer body, from the stability perspective, it is nothing but a rigid body. So what we do, we consider significant portion of the hollow volume within the submarine, and whenever we want to float it over the surface, then we pump water out of the submarine so that overall density of the submarine decreases and it rises in upward direction. Okay, because whenever you are taking water out of it, then what will be happening? Its weight will be decreasing, because the portion which you have vacated by pumping water out of the submarine's tank, that volume now is taking the space of that volume is taken by air. Okay, so which is having low density. So that is the reason that total weight of the submarine will go below, if it is going below the buoyancy force which is acting in the upward direction, it means density of the submarine is becoming less in comparison to the density of the fluid, then it will be rising in upward direction. And if you want to keep it at a constant depth, if you want to propel it at the fixed depth, then once it has reached that particular depth, there you maintain water within the submarine such that the density of the submarine is equal to the density of the surrounding water. And on contrary, when you want to sink the submarine from the surface to deeper location, then you have to pump water into the submarine. Once you are pumping water into the submarine, then what it will be doing? It will be basically increasing the weight of the submarine, and the magnitude of the buoyancy force will remain the same. So because of that, it will try to sink. And once it has reached the desired depth, then once again pump the water out to maintain the weight equal to the buoyancy force. Okay, so this is one important thing. By just pumping water in or out of the submarine, actually we can maintain its vertical position in the water bodies. Okay, so now we will stop at this point and we'll have further discussion in the next lecture.